welcome to part 2. We're going to start off with contingency tables. Okay, so we took a sample. We asked a bunch of adults if they liked this new juice, and they were in 3 different cities and recorded the information in this table. Okay, so 300 people from Omaha, 450 from Seattle, 250 from Miami, 1,000 people total. Okay, so there were 400 people that liked it, 350 that didn't. So for example, 130 were people who were from Seattle and said, nope, don't like the juice. Okay, so just pretty standard table. It's called a contingency table. And we are going to go through this, and we are going to find the probability of all of these things. So the first one we are going to do, so if we select one person at random, we want to find the person, find the probability that the person is from Miami, and yes. So there was 1,000 people asked. So if I just lined up the 1,000 people and grabbed one of them at random, I want to know what's the probability that they're from Miami, and they said yes, I like the juice, and so on. So these are the 6 things we're going to do. So for number 1, the probability they're from Miami, and yes. Well, let's look. How many people are from Miami and said yes? So let's go to the Miami column. So here's Miami, here's yes, 150 were both. So 150 out of 1,000 in the sample space. So Omaha and no. So you go to the Omaha column, you go to the no row, it overlaps at 125 over 1,000, or in decimal is 0.125. Probability they're from Miami and Seattle. Well, if you pick one person, the probability that that person is from Miami and Seattle is 0, because you're either from Seattle or Miami, and those are mutually exclusive events. So the probability of that happening is 0. Okay, so then we're going to look at the probability that they are from Miami, or said yes. So now we have or. So when we have or, we're going to find multiple probabilities. Okay, so we have 250 probability right there. So from Miami or yes. So let's look at the probability they're from Miami. So there are 250 people from Miami out of the 1,000. Yes, there are 400 people out of 1,000 that said yes. So this would be the probability of A plus the probability of B, and then minus, we have to subtract off the probability of A and B, because these are not mutually exclusive events. So we counted all the people from Miami, we counted all the people that said yes, but this 150 was counted twice. It counted as a Miami person and a yes person. So we have to subtract off. So 250 plus 400 minus 150 would be 500 out of 1,000, or 50%. Okay, the probability they're from Omaha, or they said no. So they're not mutually exclusive. So find the probability they're from Omaha, which is 300 out of 1,000. The probability they said no, probability someone said no, is 350 out of 1,000, minus the probability they're from Omaha and said no, which is 125 out of 1,000. So 300 plus 350 minus 125 is 525. So 525 over 1,000. So the probability they're from Miami or Seattle. Well, this one is different in the fact that these are mutually exclusive events. So you can find the probability that they're from Miami. The probability that they're from Miami is 250 over 1,000. Probability they're from Seattle is 450 out of 1,000, minus the probability they're from Miami and Seattle, which is 0, because they are mutually exclusive events. So 250 plus 450 is 700 over 1,000. So some people may be asking, well, do you really need to subtract off the 0? Well, here's the rule. The probability of A or B, if I could write, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So this is the rule for when you're doing or probabilities. So you find the probability of this one, find the probability of that one, subtract off wherever their overlap is if you're double counting. So if you always remember to subtract off, when they are mutually exclusive, there is no overlap. In the Venn diagram, if you have A over there and B over here, so here's the people from Miami, here's the people from Seattle, so you find the probability they're from Miami, find the probability they're from Seattle, subtract off their intersection. Well, they're not intersecting because they are mutually exclusive. So it's just a good habit to subtract it off, even though it does nothing, just so that you'll remember to do it when it's necessary. Okay. So, the probability, the at least once rule, the probability that an event will occur at least once. So the probability it occurs at least once is 1 minus the probability it occurs no times. So here is an example. So 12 light bulbs are tested to see if they last as long as the manufacturer claims they do. 3 light bulbs fail the test. 2 light bulbs are selected at random without replacement. So without replacement means you take 1 light bulb out, and so now there's 11 light bulbs, and then you take another one out. So for A, we're going to find the probability that both light bulbs fail the test. For B, we're going to find the probability that both light bulbs pass the test. And for C, we're going to find the probability that at least 1 light bulb failed the test. So at least 1. So here's where we're going to use the at least once rule. Okay, so for A, it says find the probability that both light bulbs fail the test. So both means and. Okay, so the probability that they both fail, they are dependent events. So the probability that they both fail is the probability that the first one fails times the second one fails, because both means and. Number 1 or A and B fail. So you have event A and event B. So the probability that the first one fails, so remember, in the story there were 3 out of the 12 failed. Okay, so this is the first event. But you took 1 out, so there, and we didn't put it back in, so there was only 11 left in there, and there was only 2 left that could fail. Since it's and, we multiply. So the first time around, there's all 12 bulbs together. There's 3 of them. 3 of them that will fail out of 12. You didn't replace it. There's only 11 left in there, and there's only 2 left potentially that would fail. So you multiply and you get 1 over 22. For part B, it says find the probability that both light bulbs pass the test. Okay, so here we can use the rule of complements. The probability that both light bulbs pass the test, so we can find the probability that 1 passes. So it's 1 minus the probability that 1 fails. Well, how many of them are going to fail? Well, there's 3 will fail. So, or 3 out of 12 will fail. So the probability of it passing is 9 over 12, which you can do in your head. There's 12 light bulbs. You know 3 of them are going to fail, which means 9 of them are going to pass. So the probability that they both pass is the probability that the first one passes and the second one passes. So we can find the probability that the first one passes. Well, if there's 9 out of 12 that are going to pass, similarly, the first time you take it, there's 9 out of 12 chances to pull one that passes. And then since you took 1 out, there's only 11 in there since it's without replacement. And then there's 8 potentially that would pass because you took 1 out. So you just multiply and you get 6 over 11. Okay, so part C says find the probability that at least 1 light bulb failed the test. Okay, so here, because it says at least once, we're going to use the at least once rule. So the probability that at least 1 bulb fails is 1 minus the probability of none, because if you look at all possible things, at least 1 failing is all of those things. And then this would be the complement, none, because either none fail or at least 1 is going to fail. Okay, they are complements. So the sum of the 2 add to be 1. So if none fail, that means both pass because you're pulling 2 bulbs. And we found the probability that both pass. That was 6 over 11. That was the previous example. So the probability that at least one bulb fails is 1 minus the probability that both pass, or 5 over 11. Okay, so the at least one rule is something that definitely takes some practice to wrap your head around, so we will do more examples of those. Okay, large sample spaces. So here, we're going to use counting principles from section 8.5, the previous section, for large sample spaces. So, 5 cards are drawn from an ordinary deck of 52 playing cards. What's the probability of getting a flush of diamonds? So a flush, meaning all 5 cards are diamonds. Okay, so remember, for a standard deck, there's 52 cards in a deck. 13 of them are diamonds. There's 13 of each suit. There's the ace, which is like the 1 or the highest number. 2 through 10, and then Jack, Queen, and King. And Jack, Queen, and King are the face cards. Okay, so the probability of a diamond flush. So it's the number of ways to get a diamond flush over the number in the sample space. So using the counting principles, order doesn't matter, and we're going to choose a selection. So the number of ways to get a diamond flush. There's 13 diamonds, and we're going to choose 5 of them. So we want to know the number of ways to get 5 diamonds out of the 13 diamonds. So that's 13 choose 5. The number in the sample space, well, there are 52 cards in the sample space, and we're going to select groups of 5 of them. So that would be 50 choose 5. So you would put 13 choose 5 into your calculator, 52 choose 5 into your calculator, and then divide. So it's very low chance. The probability is 0.0005. Very, very low chance of you getting all diamonds if you're dealt 5 cards. Okay, so in summary, here is a summary of the rules. Complementary events. Okay, it's what the probability of it, E complement is 1 minus the probability of B. So if you wanted to find the probability of being odd, you can do 1 minus the probability of it being even, because they're complementary events. Okay, at least one of the events, A or B. So if it's or, you do A probability of A plus the probability of B and subtract off that overlap. So this would be the case. You have A and B. So you counted this intersection part twice. So we're going to subtract it off once. The probability of A and B occurring. So if it's A, we are going to multiply. Okay, and then the probability that event will occur at least once is 1 minus the probability that it occurs no times. So this is just a summary of all of the rules that I used today. So I hope you have a good evening, and we are done.